So, let's start talking about how to prove things. A lot of times, theorems in mathematics take the form of an implication. A theorem will say something like, given thus and such, if blah blah blah, then this. And so there may be some sort of establishment of a type of element, a type of mathematical object that lies in some domain, and then say maybe some premises like, well, if this particular element satisfies these conditions, then you can conclude this fact about that element. So a lot of times it's a P implies Q kind of statement. So we're going to start by focusing on two different ways to prove P implies Q. One of them is direct proof. This is the simplest version. It's where you assume P is true and then try to deduce that Q is true. Now, this can rely not only on your assumption of P, but also on other things that you may know about the type of mathematical objects you're working with. So, for example, if P is a statement about integers, then we'll get to use a lot of things we know about integers and about operations involving integers, like addition and multiplication, and odd and even and all that kind of stuff. So there are times when there are going to be assumptions that we make and like facts that our proof relies on that we pull in from other areas of mathematics. So that's the most direct way, direct proof. The other method is proof by contraposition. Now, this is essentially just taking advantage of that contrapositive equivalence that P implies Q is equivalent to not Q implies not P, right? So to prove P implies Q, we could start by assuming not Q and then deduce not P. So that would be essentially just proving the contrapositive instead of the original one. But since they're equivalent, it also supports the original one. These are by no means the only two ways to prove things, but these are the two we're going to start with. So we're going to begin with an example here. Let's read the example. The example is let n be an integer. So n is going to be my variable here. This is the symbol that means is an element of the following set. So n is an element of z, which z is shorthand for the set of integers. Remember that the set of integers includes negative numbers, -2, negative whole numbers, -1, 0, and then positive whole numbers, 1, 2, and so on. So that's integers. Now, if the theorem is if n is odd, then 5n plus 3 is even. So how do we prove that? Well, I want to make a couple of notes first. The first note about this is that this claim is a universal claim. This is essentially saying for all n, if n is an odd integer, then 5n plus 3 is an even integer. Okay, so this claim, I didn't actually state any for all n in here, but it is implied that this claim applies to any integer n. Part of why we can say that, part of how we know that is that the n involved in the statement is arbitrary. N is arbitrary. And arbitrary means that it could be any n. It could be any integer. So let n be any integer. If it's odd, then 5n plus 3 is even. If you have a statement like this about an arbitrary integer, then since it could be any of the integers, you can generalize it. This is one of the rules of inference we learned in 1.6. It is the universal generalization. If you know something to be true about an arbitrary element of the domain, you can generalize it and conclude that it's true about all elements of the domain. So that's why implied by this, there's this idea that this is a claim about all integers. Okay. Now, the second note I want to make about this is that in order to prove this, we're going to need to draw upon some definitions. These are definitions you may be familiar with or you may not. So these are the definitions of even and odd. A number, an integer specifically, n, is even if there exists another integer k, so there exists a k in the integers, such that n is 2 times that other integer. So basically, it's an even number if it's 2 times something else. Now, the particular value of k can depend on which integer n we're talking about, right? So this existence is subject to which n we're discussing. There will always exist something if it is even, but it could be a different one. Now, the other definition is n is odd if there exists a k in the integers such that n is 2k plus 1. So essentially, it's saying an odd number is like an even number plus one more. Okay, so with that, let's go ahead and prove this. We're going to prove this statement two ways. We're going to use direct proof, and then we're going to do it again with proof by contraposition, and you can kind of compare. So the first one we're going to say, actually here we're going to say proof, and I'll put in parentheses, this is direct. All right, so first, since this is a direct proof, we're going to assume P and then try to deduce Q. Our P, let me get out another pen with a different color. Our P in this statement is this, P. Our Q would be this, Q, if then. Okay, I guess we're saying n is an integer, so we're going to take that as assumed. This is like our domain we're working in. So I'm going to have, as my first line of my proof, I'll write assume n is odd. All right, I'm assuming P. Now, what I want to do is use a definition. So I'll appeal to the definition. So I can write then n, being odd, must equal 2k plus 1 for some integer k. So k, an element of the set of integers. All right, so now we've established this k, right, that must exist. Now we don't know what k equals because it depends on what n equals, but we do know that we can work with it. It's an integer and it must satisfy this equation with n. So now we can look at 5n plus 3, okay? So now we want to try to deduce the truth of q. We want to try to deduce that 5n plus 3 is even. So let's look at 5n plus 3. I'm going to write then 5n plus 3 equals, and now I can do a substitution because I've already established that n is 2k plus 1. So I'm going to replace my n with 2k plus 1. Let's see what happens. Do a little algebra here. We're going to have 10k plus 5 plus 3 more, and that's 10k plus 8. Okay, so what's my goal again? What am I doing here? I forgot. I want to try to prove that 5n plus 3 is an even number, right? And let's look at the definition of an even number. It's even if I can write it as 2 times another integer, right? It doesn't have to be the same k, right? This k that I established here, like maybe this is a certain number, but this k could be a different k, like, a different number. So if I could write this as 2 times something, well, then that would be showing that it's even. Well, I can factor a 2 out of here, can't I? So this equals 2 times 5k plus 4, right? Now I've written 5n plus 3 as 2 times another number, which is 2k plus 4, right? Well, that number, 2k plus 4, is an integer. And the reason that I know that the reason I know 5k plus 4 is an integer is because the set of integers is closed under addition and multiplication. What that means is that if you take 2 integers and combine them with addition, you still have an integer. If you take 2 integers and combine them with multiplication, you still have an integer. So I'm going to write, since the integers, z, is closed under addition and multiplication, I can be guaranteed that 5k plus 4 is an integer, okay? By the way, just to kind of explain that a little further, if you were using, for example, division, you could not make this assumption because the integers are not closed under division. 5 divided by 4, for example, is not an integer, right? So you can divide numbers, you can divide integers and get something that's not an integer anymore. We didn't do that here, right? We just used addition and multiplication. So that's still an integer, and that means it satisfies the k that we need to exist in order to prove that this thing is even. So now I can say, therefore, 5n plus 3 is even, and I've arrived at q, right? So I started by assuming n is odd, I assumed p, and I eventually got to conclude, therefore, q. And that's how you do a direct proof. So I'll go ahead and end this one with a nice a nice satisfying QED.